Hello everybody and welcome to my channel. Today I'm going to do a different video compared with what I usually do. And I just discovered this new tendency among competitive programmers, especially at the higher levels, to post their tier lists of topics. And today I decided to take my chance and do the same thing. And I'm going to use this tier list that will be present in the description in order to point out, let's say, my favorite topics, and I will also use how nice and interesting these topics are in general. In order to do this tier list, I will try as much as possible to start with what I think are the easier topics. And then as we progress, I will, of course, select the harder topics, and I will also summarize my choices as we go. So let's begin. So we have here a lot of possible choices for what would be the easier easiest topic, and yeah, seems like we have a few ones that are at about the same difficulty, but I will start with something very simple, something like stack. Stacks are a data structure that's introductory to a lot of things. They are also very useful for a lot of problems, and stacks are also very short to implement usually. Plus, they are one of the first data structures any competitive programmer with a bit more experience ends up learning about. And I also like stacks a lot in general. So I will put it for now as A tier, but I can also move it to S tier based on what results we get. Now, since we covered stack, I will also go with queues. Queues are also just like stacks, a data structure that people tend to learn about pretty quickly. It also has a lot of useful applications together with text, but also in applications such as plot fill or other problems where we can generate stacks using queues and so on. They're also a good data structure, but I don't really feel the same kind of iconic character that stack has. But they're still pretty good, so I will go with a B tier. Now, as far as binary search goes, binary search is, I would say, easily my favorite algorithm among the algorithms and the data structures which are here at an easier level. Binary search can be applied for a lot of things. It can be applied within an array in order to find the answer, to find some mathematical function. And there also an algorithm that comes with a lot of applications in many problems. So again, a very useful algorithm and a very powerful algorithm. And a lot of things are inspired by binary search. So in my opinion, S tier, it's probably going to be one of the only ones with S tier. Now, we also have two pointers here. Two pointers are a bit more difficult than binary search, but I would say that unlike binary search, even though the time complexity when it comes to doing two pointers is always something like linear and usually faster than the binary search, and even though the implementation is usually short, there are a lot of instances in which two pointers are a bit annoying to deal with, and also sometimes they cause unnecessary bugs when we can just write a binary search and then just instead of having a log in time complexity that, of course, with two pointers, we don't have that. We have a code that's way easier to work around it. So for me, two pointers goes to C tier. Now, next off, we have sieve. Sieve of Eratosthenes, again, one of the introductory topics anyone learns when it comes to number theory. Again, an interesting algorithm. It also has a lot of usages when it comes to finding divisors, finding prime numbers, and also many other topics, even within the number theory when it comes to the higher class of problems, the more difficult ones. It can be used for something like inclusion, exclusion, or even with stuff such as Tothian function and also various combinatorial calculations. A good algorithm, maybe not as iconic as the binary search, but is definitely something that is one of my favorites. So I'm going to put it as A tier. Now, next off, I'm going to go with the constructive algorithms. Even though when it comes to constructive algorithms, there are a lot of types of constructive algorithms. There are problems that range from div3a to div1d, there are many types of constructive algorithms. And I have to say that even though at first I wasn't too much of a fan of the constructive algorithms problem due to mostly myself struggling with these kind of problems, I think they are still a useful addition in competitive programming. But again, sometimes they feel random, and also sometimes these problems can also be guessed. So maybe not the best algorithm out there, but I would say that it's pretty decent. Or also not the best method, but again, something decent enough to go within my higher categories. So I will put a solid B, or maybe a bit better than the Q, but I wouldn't put it in A, as I don't think it's anything as let's say iconic or as beautiful, at least in my opinion, compared to the other ones we put first. Now, with inversions and merge sort, and I will slowly go towards the easier data structures. Inversions are an interesting topic, and they often feature in a lot of data structure problems. So when it comes to stuff such as counting inversions or changing around values to find inversions, always an algorithm like merge sort with the divide and conquer technique, not the DV optimization. That's also later in the video. But yeah, so again, something nice, but again, not very, let's say, iconic or anything, but it's actually nice. So solid B, again, a good method, but not anything too iconic. Now, another prerequisite and also something we often have when it comes to data structures and also to DP to some extent are bitmasks. So again, with bitmasks, bitmasks can go a long way. And it actually features up twice here for some reason. So I will go with this one as this seems to be a more standard image when it comes to what I would think bitmasks are. Bitmasks are interesting. We can start with, let's say, generating subsets, or we can also go with things such as, let's say, SOSDP later on, as far as, let's say, more difficult applications go. So again, a strong algorithm, a nice algorithm, but again, not something that is really beautiful by itself. It can be beautiful in some problems, but not one of the most iconic methods out there. So again, B tier, but I can reconsider maybe to C tier if it's not that good. Now, let's start with some of the data structures or methods relying on data structures, the easier ones at least. I will start with segment trees. Segment trees are again one of the better data structures out there, and they show up in a lot of variations. So we can go with the normal segment trees, the lazy propagation, merge sort tree, wavelet tree, and there are a lot of different ways we can apply segment trees for. Even Lichao can be implemented with segment tree from what I see here. Also, I've also seen heavy light decomposition that has a segment tree part in some implementations. So again, and it's also very flexible. So I would put it as S tier just because it's one of the most iconic data structures I can think about when it comes to competitive programming. Now, Fenwick trees are a bit of a wild card here, as for example, I can say that I'm a big fan of Fenwick trees. I even made a video on Fenwick trees 3 years ago. I love this data structure, but it has a major problem by itself. Also not flexible at all. You can only use it for a small range of problems involving mostly sums and reversible things. And even though it is, let's say, faster as far as the constant factor goes than the segment tree, its narrow usage makes it way harder to work around with than with the segment tree. And this is what most people do. Even though I like Fenwick trees, I often teach Fenwick trees together with segment trees as far as data structure goes. I will still put it at A tier because, well, it's not something that is used by too many people and you don't really need it for anything specific. And at the second thought, I will just move it to B tier because I like it, but it's not something too essential, which is a bit unfortunate. But whenever the day will come, maybe if Fennec trees will be used for something else, I don't know. Now, the next one, sparse tables. Sparse tables are a bit of an interesting one too, even though they can range in usages from they are used for things such as binary lifting, but also when it comes to range minimum query data structure, we can also do it with sparse table. There are also other data structures that rely in some way or another on sparse tables. Again, a solid data structure, but also a data structure that tends to consume a lot of extra memory, and it's also part of the broader data structure set. Again, I will put it as B tier. I don't think it's really the uh, sorry, as A tier for now. It's a good one, but not the most solid one out there. Next off, we also have binary lifting. Again, binary lifting, another data structure or method I really love. Uh, it's very elegant. It can be used in order to find the LCA. It can also be used in order to find, let's say, various tracts. And I will also rate together binary lifting and LCA because there are two methods that are often related to one another. And even though for LCA there are other methods of doing it, uh, there are still applications for which maybe it's not the most versatile out there. Also, it's a sparse table, so it also has this rather fixed idea. So I will go for now with B tier for both binary lifting and LCA because I will rate them together. I'm honest here. They are similar enough, or at least I would say that given that I write LCA using binary lifting usually, I believe they are to some extent similar enough to be rated together. Now, before we move on to other data structures, I want to switch a bit to some kinds of DPs to also have a bit more of a variety. First off, knapsack DP. Knapsack DP is probably one of the first types of DP any competitive programmer learns about. And it has a lot of variations. Again, a method I really love talking about. I also made a video on knapsacks a while ago. And also it has different kinds of optimizations, which are all nice. Again, very iconic, very nice, can be modified in a lot of ways. So I will put it as A tier, solidly. Solidly A tier, a pretty good one. Now, DPs on tree, they're also pretty nice. Now, of course, uh, often they get pretty repetitive, and I would say that I haven't really seen recently that many beautiful DP on tree problems out there. And another issue is that when it comes to DPs on trees, once you know how to solve a few types of problems, they get very boring fast. So not one of my favorites, but I can see some flashes of brilliance when it comes to DPs on tree. I will put it at solid C tier for now. Again, not something that's my favorite, but also I can see why they are liked by people. Now, when it comes to DPs, there is also divide and conquer DP. Sorry. Again, when it comes to divide and conquer DP, an interesting optimization, it can speed up a lot of, not a lot, but some types of DP, but my issue with divide and conquer DP is that it's very hard to be too original about divide and conquer DP these days, since a lot of the optimizations come down to the same things. But it's usually pretty nice when you see it. So I will put it as B tier, as it's not that bad. Now, from what I see here, we also have some over subsets. So SOSDP. SOSDP, while I know that the technique is very interesting, and maybe for the more seasoned competitive programmers out there, or I would say more like the higher level competitive programmers out there, it's also easier to understand. For most competitive programmers, it's actually a very difficult algorithm, and it often feels like you just black box it, as you just implement it once or twice, and then you forget about it until you randomly see something that looks just like SOS. So for me, C tier, not a bad method, but not my favorite either. Now, convex hull trick. Convex hull trick, unlike other optimizations, I actually will rate it higher, as I like it a lot. But at the same time, it's also an optimization that was covered in many ways by many people, and it also has this interesting flavor about it. So I will rate it as B tier for now, but of course I can change my opinion based on how the distribution will turn out. Now, let me see if I forgot any other type of DP for now. Uh, for now, seems like I haven't, but we can look back and see. Now, let me finish off with some of the dark horses from here. So, as far as hashing goes, hashing is not very interesting in my opinion, as it often feels like you do the same thing, as you just use that prime base, uh, that prime base, that prime mode, and so on. So again, I will rate it as D tier, not something I really like. But again, it helped me win this shirt, so uh, it has some credit to its own. But again, not a thing I am really fond of. Again, probabilities, random, and random algorithms, they're, I think, interesting. Even though they don't show up in a lot of problems, and of course, as the name goes, they feel random. I can see the beauty behind randomization problems. I wish there were more of these problems. They used to be a while ago in Code Forces, but again, not something that's really part of the broader focus competitive programming has. So B tier for me, maybe around here. Now, we also have the broader number theory. If I said that this sieve is an iconic one, the rest of the number theory doesn't really feel that interesting, as you tend to have a lot of formulas that often repeat. You also, I think, stuff like Chinese remainder theorem also comes here. So, and also the various combinatorial formulas. So again, it gets boring after a while. But again, not too bad. I will put it as B tier, maybe around the middle. I think it's around where constructive algorithms are, in my opinion. Now, what else do I see here that feels a bit like a wild card? Well, for now, I don't really see anything. So I will go with the geometric stuff. So geometry by itself, I don't really like it. Few people like it, and it has some beauty in it, but honestly, it's going to be one of the things I will put as D tier in general. It's very ugly to deal with the cases. Sorry for the geometry fans out there, but barely anyone likes geometry. There are many other topics which are better. So I'll put it as D tier for me. Line sweep, however, is a bit better. I've used it in a few problems and it was actually rather nice. So, but still, it's part of the broader geometry spectrum and this is going to ruin its score in my eyes. So I will go with C tier. I can see the beauty about line sweep in some problems. I solved a few problems which were nice, but not one of my favorites. So Then again, we now that we covered most of the geometric stuff, given that we talked about random, I will also talk about probabilities. They're also all right, I would say, but not one of my favorites, but they show up in some nice problems. So I will put it as solid C for me. Now, uh, now KMP, so in order to wrap up, let's say, the more known algorithm, as we will mostly be left with data structures from what I see, and also BFS and DFS, so, and the graph algorithms. KMP is a nice algorithm. Of course, it has a lot of usages in real life. It can be used for pattern matching, many cool applications, but it often feels random for many people. And as such, I'll put it around C tier. Now, I will go with BFS and DFS to start the graph part. Uh, BFS and DFS are two techniques that are complementary to each other. They are also the bedrock of any graph book, and they're also very useful in many problems. So, and they are also short in implementation. So I'll put them together as A tier. There is not that much of a difference between them for the most part, but of course there are problems in which we tend to apply one or the other one. Now, Dijkstra is a nice algorithm. I actually find Dijkstra nice as an algorithm, but lately it feels like just about anyone knows what Dijkstra does. And I haven't seen many problems with Dijkstra anymore these days. So I will put it as low B tier, but it can also be C tier. Again, useful algorithm, but it gets boring fast. Now, as far as let's say we're starting to get a bit into the more difficult graph algorithms. I will go first with something like just what I will go with something like bipartite matching. Bipartite matching again, it's a decent algorithm. I can see its merits, but I'm honest here. I haven't been too big of a fan of let's say the graph algorithms, but again, it's pretty nice given that for bipartite graphs we also have n square root of n algorithm, so that's cool. Now I will go with the rest in order, but first I will want to go with Euler Tour. As Euler Tour, I think is somewhat more decent than the other algorithms left here. It's rather nice, but again, it gets boring fast. So I'll put it as something like B tier, but without too many credits to its own. Uh, now, UFDS, small to large, it's actually a nice technique, even though it doesn't show up that much. I know many people who are fans of this technique. So I will go with B tier, somewhere around the middle, as it's actually a good technique. FFT polynomials, well, it's math to the steroids, as some would say. Most people just end up copy pasting their FFT template. There are also people who just use entity, which is FFT, but when modulos are of a certain format. And I don't know anyone who actually enjoys FFT. Again, D tier, just like with the geometry. Bitmask, again, I put it already. Ahokorastic, again, it's just camp you wanna try. And well, there is not much to say about it. It's just a long implementation without too much of a usefulness behind it. It has, of course, usages in real life, but not that much in competitive programming. Matrices and matrix expo, again, some DPs can be solved using this. They are not too bad, but again, not something I really enjoy. So C tier may be close to the other math methods. Lee-Chow tree, it's useful for convex Hall trick, and convex Hall trick is something I rated highly. And it also has some variations of segment trees and other data structures. So given that it's used for interesting things, I will also rate it rather decently. I will put it around the Fenwick tree, just because it's a data structure that looks just like these ones. Now flows, even though I don't have much experience personally with flows, I think they are iconic enough in some way to not get that rating that's near the bottom. But again, once you know how to generate the graph, things get boring fast. So somewhere around B tier with the other graph algorithms, maybe. Suffix string data structures. I know there are fans of the string data structures, but personally, I don't enjoy them at all. Uh, Again, these are the kind of algorithms that are way more useful in real life than they are in competitive programming. But as far as competitive programming goes, I will put them around the C tier. There's not much new we can do with them anymore. Trips, it's actually a common joke, or not really a common joke, but a common theme about people learning all kinds of data structures that boast about them, and trips is one of them. And well, trips are all right. They have many usages, but well, it's a data structure that's way too long to implement, and you don't really end up seeing it that much in contests. So again, top C tier. So uh, not something I really hate, but something quite all right. Now, uh, strongly connected components. I actually like them, even though just like many other graph algorithms, it's very hard to innovate from. They're all right. And once you see them in problems, you kind of get their main idea. And the same will be when it comes to BCCs, but I will rate them slightly differently. The big advantage when it comes to SCCs is that they're also short when it comes to implementation. So again, something I like. And they're also quite cool. So I'll go with SCC for A tier, somewhere around the DFS and the BFS. But when it comes to BCC, they're in arguably direct, undirected graph version. While they do similar things, for some reason I don't like it that much. Again, very hard to innovate, but it's all right. I think it's quite all right. I will put it around B with the other three data structures. Now, dynamic connectivity, well, in competitive programming, it's usually something people learn about just to know one more algorithm or to solve some random 3000 problem on code forces. So again, one of these, let's say, hardcore data structures, but it has usages in real life. Don't get me wrong. It's actually a good one, but not maybe what you would expect when it comes to competitive programming. AVL3, again, just like with the other advanced data structures, people just learn them as they are. Of course, there are variations of all these kind of binary search trees, AVL trees, balanced, whatever, in the STL, but just implementing them by themselves is not something I expect to do anytime soon. And most people don't do that either. So again, C tier, they are useful, but not very attractive. TrueSat, an interesting one, but well, even though its premise is nice with having the SCC setup and doing the 2 times n graph or whatever it is, uh, it's not something you see in problems. It gets pretty boring. But I can give some credits that, well, it can have some useful usages. Now, as far as heavy light decomposition goes, it's a lot of implementation without too much of a result, but you can do some nice queries on a tree. So I won't be too harsh about it, but not very generous either. I will put it around B tier because basically heavy light decomposition is segment tree combined with LCAs, or depending on the implementation, of course. So around B tier here. Last but not least, centroid decomposition. Actually, I think it's another algorithm or method I really like. And it has a lot of usages in Olympiads. It can also be used in other instances too. And there are a lot of interesting problems that are created to this day, in my opinion. So I will go with S tier to have another one here. I actually like it a lot. And now that I think about it, I will also put stacks in the S tier, but move some of the other ones in the low A tier just to get a bit of a higher average. And of course, with bit masks, I will move them just where bit masks were, just where other bit masks were. So here we are. We have this tier list, and I think it's a fairly balanced tier list. I have algorithms of all types in all kinds of tiers, and I think it's something that it's worth using. So thanks for watching this video. I hope you enjoyed it, and see you next time. Cheers.